So in the last video, we learned about instantaneous rate of change, and we saw how we could use a special limit of a certain expression in order to find the slope of a tangent line, and that slope of that tangent line would give us basically the instantaneous rate of change of our function at a specific point of interest to us. So moving forward from that, we move on to a very important idea in calculus, which is the derivative. What a derivative is basically it's an expression that we can use to calculate the instantaneous rate of change, that slope of the tangent line of our function at any given x values. In other words, we can use it, or basically it gives us the slope of a function at any point. So how exactly is this different than what we were doing? Well, basically what a derivative, or like I mentioned earlier right now, is a derivative is an expression, meaning that we can plug in our x value into this expression and it will output the slope. So the way that we denote a derivative is using this notation. We normally say that this is f of x, right? F of x. Well, the derivative of our function f of x, we would denote it as f prime of x. This is, as simple as it gets, is how we refer to the derivative of our function f of x. We can do this in more ways than one, really. We can say this is the derivative of f of x. We can also use what's called Leibniz notation, where we write dy dx. This is the same thing as this. We can also simply just write y prime. This also refers to the derivative. So all three of these are equivalent and all mean the same thing. So again, why do we use the derivative? Well, when we're given more complex functions that aren't linear but may have varying slopes at different points along the function, a derivative becomes necessary in order to figure out the slope at various different points along the curve. So how exactly do we use a derivative? Well, basically, if we're given a function, our f of x, we find the derivative, giving us this expression, f prime of x. It's going to be an expression into which you plug your x value. So if you take your derivative, plug in some x value into here, it will output the slope of our function. It outputs the slope of our function f of x at this point x. This is different from what a regular function does, right? Just to clarify, we know that if we take any regular function and input some x value, what we get is a y value, right? We plug in this value of x into our function and it outputs a y value. This is different than what the derivatives expression is doing. Once we plug the value of x into our expression for the derivative, it outputs the slope of the function at that point, not the y value. So just making that clear. Then, it's an important distinction to make. It can seem similar. The notation also looks somewhat the same, right? It was just the prime is the different thing, but you must recognize that they're really talking about two very different things here. So now, what is the definition of the derivative, right? And that's important to know when I say the definition of the derivative. And I don't just mean in words what that is. There is a formal mathematical definition, and oftentimes, again, on the AP exam, as well as in Calc 1 classes in college, they ask you specifically to find the derivative using the definition of the derivative. So what is this definition? Well, it seems to be glitching a bit. Definition of the derivative. Definition of the derivative. Well, you'll notice that this definition of the derivative looks very similar to our instantaneous rate expression that we saw in the last video. Really what it is our f prime of x is going to be equal to the limit as h approaches 0 of f of x plus h minus f of x minus f of x divided by h. And so really this limit here is going to give us an expression. If I solve it for this limit, it'll give us an expression that will calculate that instantaneous rate of change, the slope of that tangent line, for our f of x at any given x value. Solving this limit gives us that expression. So let's see exactly how we can use this in order to find some derivatives and figure out the slopes that we were talking about. So if this is our function here, our f of x is equal to x squared plus 3x minus 1, we now need to find our f prime of x, our derivative of our function f of x, using the definition of a derivative. So how do we do this? Well, first we need to build this difference quotient here, right? We know that the definition of our derivative, just to remind ourselves, is going to be the limit as h approaches 0 of our f of x plus h minus f of x divided by h. So what you're then going to have to do here is every time that you see an x, you're going to have to plug in an x plus h for this part. Very similar to what we did in the last video looking at instantaneous rate of change, we're going to need to construct this function f of x with some slight modifications here. So what I mean by that, again, is remember, first we have to do this f of x plus h. To do the f of x plus h part, every time here in our function that we see an x, we substitute or we replace that with an x plus h. So let's start, right? The limit as h approaches 0 of our f of x plus h, so that to get f of x plus h, that is going to be x plus h squared plus 3 times x plus h minus 1. And this, from this we subtract f of x, right? So for that, we just subtract our entire function as it is. So that's x squared plus 3x minus 1. And this divided by h. So now we can just simply expand and then simplify the numerator here, right? This is some basic algebra here. So our x plus h squared simply becomes x squared plus 2xh plus h squared. The 3 times x plus h becomes 3x plus 3h minus 1. And then we distribute the negative here, so minus x squared minus 3x plus 1. Here we can then continue to simplify, and if we do so, that gives us our numerator 2xh plus h squared plus 3h, right? Our x squareds cancel out, our minus 1 and plus 1, our plus 3x and our minus 3x. And this is just going to leave us with 2xh plus h squared plus 3h. And remember, this was all over h here. And so then what can we do here? Well, we can simply remove our h, or take an h as a common term in our numerator. So that's h times 2x plus h plus 3 divided by h. This allows us to cancel the h's out, and we go back to our initial. You should also, I guess, remember to write the limit as h approaches 0 during each of these steps. Just in order to conserve some space here, I decided not to do that, but make sure when you're showing your work on an exam to include the limit as h approaches 0 in each of these steps here. So what you then remain with is the limit as h approaches 0 of 2x plus h plus 3. A little direct substitution will then yield us our answer of 2x plus 3. This is the derivative. So basically what it is, like I told you, it's an expression, right? It's not going to simplify any more than this. This is what our expression for our derivative is. So let me just clear up some space here. Well, so that is our answer. Let's clear up some space. So we know that this derivative, f prime of x, is equal to 2x plus 3. So what that means is, if we plug it, we can take any value for x and plug it into this derivative, and that would output to us the slope of our function x squared plus 3x minus 1 at that specific point. So you can see how that can be very useful and save us some time here. So this is basically how we can find the derivative using the limit, using the definition of a derivative. Let's now look at one more example. Feel free to pause the video and try this yourself. It is very similar to what we did, just a different function. So looking at this example, we're trying to find the derivative for our function f of x, which in this case is 1 over x. So first, again, we set up that difference quotient here. Remember, the f of x plus h minus f of x over h. So in this case, our x plus h, we just need to plug in an x plus h every time we see an x for our function. So that would give us the limit as the limit as h approaches 0 of 1 over x plus h minus, f of x, so that's just 1 over x divided by h. So here we can then try to, as we did before, simplify this further and then just find the limit. So in order to simplify here, we can combine the fractions in the numerator firstly. So we can start by doing this 1 over x plus h minus 1 over x over h. This becomes x minus x plus h over x times x plus h, right? We're trying to get a common denominator here. This leaves us with negative, because again, x and x minus x plus h leaves us with negative h over x times x plus h. If you forgot that this whole thing is also over an h here. So let's just clear up a little room here. Bring this over here. So we can rewrite this as negative h over x times x plus h times 1 over h. Doing that is smart because it allows us to cancel out this h's here. And this gives us a negative 1 over x times x plus h. This is something that we can take the limit of a lot more simply, right? A lot more simply, because we can see that the limit as h approaches 0 for this expression here can be solved using direct substitution. Plugging in a 0 for our h gives us negative 1 over x squared. And this is going to be our derivative. Our f prime of x is equal to negative 1 over x squared. So this is basically just how you proceed with these types of problems. Nothing too crazy here yet. We are simply just doing what we did for our instantaneous rate problems, really. We're just plugging in a very slightly varied version of our function into this limit definition, and by using a little bit of algebraic manipulation and the tools for limits that we've learned in previous videos, we can simply find our derivative here using the definition of a derivative. So that is what we learned in this video, how to use the definition of derivative in order to find a derivative. Hopefully you found it useful, and if you did, please show your support by liking and subscribing, and leave in the comments any questions that you may have and what you'd like to see for future videos, and I'll see you in the next one.